Apparently, depending upon who you ask, there's maybe 26 dimensionless constants in nature. Some folks say there's 44, because we all know 42 explains a lot, but I claim 44 explains more. Here we go.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one rule ad. I don't think it rules them all. And it might be just hyper-ruleal turtles all the way down.
Yes, it's on the back of an infinite number of hyper-ruleal turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So I totally realized that I was a lot more efficient actually not trying to like stream all this and actually go through some constants and stuff. It's like, oh, let me learn to use the Wolfram language. Because before, like a lot of stuff in like Thad's book, which I actually remember in the description below this time, available on Amazon. A lot of times it's like, okay, I'm looking at this, I'm like, that's cool. That's great. What does it all mean? Unless you've run the hyperbolic vortex equation, you have J 1 through 4 and everything, and then it also has the two imaginary inches as well, which apparently is very useful. Yeah, basically you actually need to derive everything out there. I've done some select things, and then actually going through, I'm like, oh my god, this is some of the most beautiful math I've ever seen. But what am I talking about here? Okay, this was, I believe, this is the rotation of the first, the Planck time boundary. And you're looking at over here, I'm like, oh, pi to the e times the blah, 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 equals 44. Some may say that's how you could try to, if you're going to attempt to decode a realm of persistence, yeah, you could decompose it to 44 things, because if you're going to be utilizing it, at least from a 5-dimensional, and again, particular dimensions, not always spatial. One of them is the Planck length, which is space, but basically, and again, ignoring angle, you could say that's kind of, okay, we're using a protractor here. Dr. Weinstein said, rulers and protractors are important. I digress. But if you have time, space, mass, charge, and temperature, you can essentially make up pretty much everything else there. Or at least pretty much every time I've gone in, there's like, well, look at these things. I put it into Wolfram Alpha. What are the dimensions? Oh, it's time to the -1, this, mass, blah, blah. Put it into Planck units. Like, oh, this seems to translate. It appears to be a coherent set of units. Apparently, that's important. If I just look at this, I'm like, okay. Oh, look at this. Oh, I'm thinking of the other one. But, oh, that's a lot of decimal places there. Then you get answers like, okay, the solution to K, which is, I believe, the rotations. All right. K equals N. N equals what? Oh, it's the set of integers. I could go on for infinity. But allegedly, it's a countable infinity. Apparently, that's important. Yeah, thank you, Vsauce. You get solutions like K equals plus or minus 2. That is interesting. K equals plus or minus 1. K equals 0 or K equals 3. That seems very convenient that those things line up there. Again, some beautiful math, but I digress. So we're going to go back to our other thing here. We go to, oh God, we gotta go back to the beginning of the book, because yes, should totally. Oh no. Okay, we'll just scroll through. All right, where are we? Oh God, there's so many beautiful things going on here, and attempting to gain an intuition. That's why it's like, okay. I sit back, I'm like, what if Professor Einstein had Wolfram Alpha? Somehow I think there would be more work done. I think if anybody had Wolfram Alpha, it's like, oh, you don't need to do it down on pen and paper. That's cool. You can totally do that. I think I forget how to do long division. I still understand the concept, but it's been a while. It's been a while. Okay, so we go through. Where are you here? Oh, it is. Oh God, let's scroll through the whole book. Hold on, we'll stop sharing this. Free up some computational power there, which is very interesting. And apparently, if this is like a code, yeah, you should be able to help work it. Oh God, again, it's one of those things you look through, you're like, okay, this is cool. I kind of understand. I read some words. Do I understand what the words are doing? I feel like this is why we used to have homework problems or class problems where we actually go through it. You could actually start to get an understanding. Okay, here we go. All right. We go back to our friend here. It's 44. The second edition. Again, nobody ever docks himself in the answer. The constants in we skipped ahead a fair bit. What? Page 57 of 163. Okay. So far, we have this. Oh, up this here. There we go. All right. So far, we have discovered that the minimal arena, internally defined as the minimum possible volume complement, the hyperbolic figure 8 knot, externally counterbalanced as the n hypersphere of maximal volume, decomposes into 5 unique bases: time, space, charge, mass, and temperature, with sharply defined boundaries. Yeah, they're looks very fractile. Looks very fractile. Yes, Jen, Kali. Yes, a lot of people's intuition, and even I forget the gentleman's name. Very interesting. I think a lot of us, as Professor Wolfram has said, we're kind of talking about the same things. We're just kind of going about it a little bit differently. But I'm seeing a lot of folks homing in, and I tend to think, again, just pure speculation from a dude on the internet. I think it's just part of the wave function cosmic. The Planck constant said that the external charge and mass boundaries of that arena partition into the exact charge and mass values that define the fundamental particles of matter. In this chapter, we notice minimal arena's 44 unit arrangements define the constants of nature. Oh. To unveil the geometry of each constant of nature, we think of them as binomial combinations of a primary partition action, A sub P, and a primary intersection of boundaries, B sub P, and a terminal action, partition action, A sub T, on the minimal arena's terminal boundary. And that's the break in, no, it's not the break scale symmetry. That's the it was Planck mass times Planck length divided by Planck charge squared. So basically, it's 10 to the -7. So like 0.00, like 6 zeros, and then a 1, which is interesting, which also corresponds to Ampere's constant. Yes, electricity, magnets. How do they even work? I say we're getting closer. So basically, the universal binomial factorization prescription. Yes. Since the terminal action of this balance doesn't get expressed until the 7th digit, this equation can be solved in pieces. So essentially what you're doing is you're breaking it up into pieces. You literally go in, you utilize Planck units for the dimensions that you're attempting to express there, and you get a good guess. Like you said it, what are our observations? Let's set it to this. Okay, we got it there. And then you break it up, and basically you're trying to match it, and then you keep on getting closer and closer. And if you're looking for, and again, some say that elegance is very important. It doesn't necessarily, well, it depends on how you're expressing it. I mean, if it's computationally equivalent, combinatorically equivalent, it doesn't really matter. But just for, basically, if you see an answer, it's like, here's some big thing with all this. And then the other one, it's like, what's the difference? Well, it's got the base factors that we're listing, and then 2 pi. It's probably a good approximation, especially if you're dealing with rotation operators and stuff and things like that. So as we can see, the Planck length times Planck mass times Planck charge squared, 10 to the -7. This balance first solve for the primary action, the primary boundary, and then return to the full equation to solve for the terminal action, A sub t. Step 1, temporarily set A to 0 and construct the primary boundary from the dimensions of the constant selected from the minimal arena's primary partition boundaries. Okay, we got those there. Okay, step 2. If A of P is not 1, then solve for the terms of the primary partition parameters. Pi, J1, and J(r). It's the hyperbolic radius. We skipped that part. Plug the solution into AB, all sub P. Back in the universal binomial factorization prescription, solve for the terminal action A. That constant of nature in terms of the minimal arena's derangements. D0 through 4. And it's terminal partition parameters. Pi and J 0 through 4 and R. Let's work through 2 examples. So this balance of dimensions for sense of speed of light has dimensions of meters divided by sense primary boundary equal to the natural boundary length of the Planck length divided by the natural boundary of time, Planck time. Okay, get that. 2.8 times 10 to the meters per second, 8 meters per second. These numbers match the measured molecular speed of light. So for the first 7 digits, that set to 1. To finish, we plug A of B back in the universal binomial factorization prescription and solve for the terminal action of the speed of light, A sub t, equals negative pi divided by the rotation from balance, the derangements ratio for D1 times J sub R, this was the radius squared there. All right, where then we set it equal, okay, Planck length plus that. Oh, looks like we're trying to get a better guess of what's going on. All right. So yeah, we got that stuff there. Go through and yeah, so we can see it's there. And is the number unique rotations partitioning the minimal arena? Okay, so we got our 5 for time, space, mass, charge, temperature. B is the break and scale symmetry, so 7 circles there for our circle. We're going to divide up equally. So we got the temp 8. Okay, so realistically, you're looking at this, you're like, I mean, if some dude like me can start to work through this as a dude on the internet, I think this is very useful. Especially if we assume the hyperbolic vortex equation is correct. It's a very beautiful thing. If you got the fine structure constant, you can basically derive everything else. I'm just saying. Okay, trying to think. Oh God, I haven't even done all these yet. I'm so bad. Okay. Every constant of nature is a binomial union between a primary geometric action on a primary arrangement of its boundaries, the construction of which is determined by the dimensions of the constant, and a terminal geometric action on the terminal boundary on the minimal arena. Yep. Planck length, Planck mass, divided by Planck charge squared. Again, that is very interesting. Let's charge. We continue. This universal binomial factorization prescription allows us to geometrically unveil every constant of nature. Okay. Got some things in here. Oh. Let's find structure constant, J1 squared. So basically, as Professor Fine would say, essentially the true fine structure constant. It's like 0.085, yada, yada, yada. Oh, that seems pretty simple once you have that. Elementary charge, J1. Oh, times the Planck charge. It's the charge of the electron. The gravitational coupling. Oh, look, you get the 5 structure constant. Sub G equals mass of the electron divided by mass of the proton squared. It's very interesting. Okay, we're gonna go. Let's do a couple of these real quick. Okay, so let's try find structure constant is, okay, we totally have this bookmarked because it's been, oh no, don't open up Google Hangouts. It's been so long since I canceled you. I mean, I'm not saying it was my fault, but I saw it's like, wait. So you're saying the host can just automatically turn on a person's camera without the consent? That seems like a privacy concern. I tweeted at YouTuber a lot at the time, and I'm like, and I think Google, I'm like, is this legal? It's like, well, not without a lot of warning. 2 weeks later, they announced it was going away. Yes, this is how my mind works. Okay, so, all right, we go over here, we bring it up, boom. We got our window here. We go to Wolfram Alphas. All right, welcome, Mark. Welcome, Ark. Yeah, no, you're fine. You're fine. You can continue being the celery king. But all right. So we have this. Is this really that scary, Ark? Come on. 1 over x plus a. I'm sure you played with a graphic calculator. You can run all these other fancy things streaming. You type some letters and stuff and things with the Wolfram Alpha. I'm just saying, I think you might find it useful. Again, if it's your thing, if not, do whatever you got to do. 1 over x plus x cubed, divide by 2 pi. Oh, that's a circle. Equals I raised to the I. Some reason allows us to take the square root of -1. Yes. And then we raise that to negative pi divided by 2. It's a twist going the other way, a circle. And then we subtract this number out. What's this number? 2.17, yada yada, times 10 to the -8. That happens to be the Planck mass. The fundamental unit of mass that, about the mass of a mosquito egg or a human eyelash, somewhere in there. Very interesting. Something within our realm that we could actually kind of like perceive and try to understand, even though it's really small. That happens to come out, and yeah, we get all this beautiful stuff. And then we get Joe 1 here. Oh, that looks kind of like the true fine structure constant. Well, if it was a fine structure constant, we square it'd be like 0.0072, yada yada yada. All right, let's see what happens. Oh, 0.0072973525572 yada. Oh, it's very interesting. And again, I'm just like, if it was just this, I'm like, okay, it's kind of cool. You can do whatever you want. That's kind of nifty. But utilizing what gets derived in literally this, well, let's say it's a grimoire of power. I really don't think there's been this much power in something since the old Zanzularian Hero Charm and Talisman of a Feral Power from World of Warcraft. Yes, 3-minute mage. I'm just saying that he goes through them like, you don't really need a lot of other extraneous things. What are we using? We're using pi. We're using e. We're using all that other stuff. Okay, let's go to the other one. What's the elementary charge? Okay. I'm going to take Joe 1, so we'll take this. Okay, we're going to multiply it by charge. Oh. It's 1 elementary charge. How very fascinating. I should actually totally take these and, yes. I'm copying them into the notebook because I have a little other notebook here. You actually, I think I see what that is. Like, if you can have this. If you actually want to see what's going on, you got to do it yourself. It's the way maybe it should be. Okay. Equals and to recharge. I really should just put this all in Wolfram notebooks. Things to do. So much time, so little. Strike that. Reverse it. Okay. What's the other one? Oh, gravitational coupling. Okay. Coupling is 1.7518 times 10 to the negative 45. Ooh. How could we get that? Mass of the electron divided by mass of the proton squared. Okay. Mass of electron divided by mass of proton. Wrong way bracket. Oh, carrot up. There we go. Ba-ba-ba-ba-ba. Oh, did I do it wrong? I did it. Electron per proton. Oh my god. I missed adding something, didn't I? It's very interesting. It's close to the speed of light. Why? And again, you don't do something right, it'll let you know. Okay. Let's keep these tighter. Boom, boom. Extra brackets. Bracket, some may say. Oh. Oh. It's mass Planck, isn't it? This is why I think notation confuses people. Like MP, oh, that's mass of the proton. Oh, see, there we go. See, we go. It was user error. That's the electron. Blank mass. Square that. Oh, 1.7518 times 10 to the negative 45. Oh, that's what we were looking for. Groovy. All right. And to be fair, once you start breaking it down, you just derive everything. I'm just saying, looks like 175 pages with all the extra appendices and stuff. If this is this type of stuff you're interested in, some may say it's like a new kind of science. Shout out to Professor Wolfram, because we can. And again, it has not yet been proven.
The world exists on the top of a giant turtle.
Let me see. Is there something else we can do really quick? Oh, let's do the muon. I think we can do that. That's another section. All right. Hold on. Stop sharing. Free up some computational power. Not gonna go much longer. Yeah, that's cool. We got you. We've got you. The mass partitions. That's pretty groovy. I'm gonna go to charge. See, this is what happens if you're on a mission and you're grinding out on Wolfram Alpha and trying to learn as much as you can, and you do it with the same passion that I essentially did for playing World of Warcraft. God, the amount of time I had slash played, I could have earned a doctorate. Or try to do something useful like this. Just saying. All right. Charge partitions. Where are we? Muon. Oh, this is why I personally prefer PDF. But then again, sometimes you just got to put in the work. Also, then you want to break those rules and stuff. Okay. Beautiful, beautiful thing. We go back over. Page am I on? Oh, there's so much pretty stuff. Let me actually just share some of this real quick. Just because you're going through, you're like, oh my god, It seems so crazy, but it works. It works. I mean, look at the fractals. Oh, there's that. Okay, I think we're at. Where are we? No, we already did that part. No, help. Okay, we're not going to do that. We'll do. Oh my God. I'm so ill prepared. Well, these things happen. Where are we? Second edition. Do the. Go to. Might want to let me go. Oh, location. Page. I want to say like 71. Okay, radius. Okay, we need to go up a little bit and we'll get charge. That's the neutron magnetic. Here we go. All right. Share screen. Boom. That's the mu1G factor. This has been updated. That's what it is. The more elegant fit is after. By basing on the observation, it was a little bit more this and that, but I'm like, oh, well, Riemannian's first continued fraction constant. There's a lot of pies in there. It's going to fight like a circle each time. It's pretty groovy. Okay, the mu1G factor. Square root of B, which is 7. CR1. We square that. There's J1. Mass of the neutron. Mass of the I think that's tau. I believe that's no. Tau is the other symbol. Plus 1 secant cotine cotangent secant times cotangent times 2 gamma times n5 divided by 7, and then thermal bound reaction. Okay, so let's do this. Let's go to our friend Wolfram alpha. Boom. Sometimes you might gotta look this up a little bit. It's a natural language working thing, but again, you need to know what you're talking about. Okay, so first let's look up this. So Manugen first continued fraction. All right, so his fraction is 1 over. Believe we want mathematical definition. Nope. There we go. Generalized continued fraction. How about fraction? Natural language. Might be under some other name. Da-da-da. Infinite series, continued fractions. Continued. There we go. Da-da-da. Include almost all integers. So, believe this is -2, blah, blah, blah. Okay. Our first one, that's what we want. Okay. So we're gonna, first one, that's groovy. So yeah, this looks like what we have there, 1 over e, -2 pi, dot, dot, dot. Okay. So we've got the thing that I was a little confused on how to write there. All right, so we go space and negative square root of b, which is 7. Multiply it by that term right there. Okay. CR1. Okay, and now we square that term as well. Okay, let's keep it together. Okay, we're keeping it together there. And we multiply it by Shoutout. So just quick new tab, boom. Da, 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 da. Okay. Right to the hyperbolic vortex equation. This is why it's very useful. Okay, we get Shoutout. Okay, where are we? So we then multiply this. Brackets. Okay. That, and then mass of the, where are you? Mass of, I'll go over here. Mass of tau. No. Mass of, no, let's get mass of the mu. Oh. Again, we get the, yep. Okay. Just making sure. Okay, so that, we apply that by mass of neutron by mass of muon okay. And then let's apply that by the second part of the function. This is why we separate it out. So 1 plus secant bracket cotangent and 2 times big gamma and 5. Okay. The cotangent, and we want to keep this 2 gamma 5. Divide that by 7. Wrong way, which is breaking scale symmetry. Okay. So brackets there. Brackets around the cotangent. Okay. And the breaking scale symmetry is S length Planck charge. I used to -2 since we're doing a division. Bundle that. Bracket should work. Go. Wolfram Alpha. Let's see what I messed up on. Where was that? Oh no. What is that? Square root of 7. Oh. Where did I forget the bracket? Okay. Negative square root of 7. Oh. No, that's not what we want there. Maybe. This is what happens if you don't put, sometimes it's just easier to put it in the numbers. Okay. See if that helps at all. Apparently we triggered it with some other things. No. We forgot to bundle Huntington's thing. What a noob. Not him. Because now we was going to try to do all these other stuff and things, and now it's actually, oh my god, I'm still getting it wrong. I'm still getting it wrong. Okay, that's squared. Sometimes the n there. Here. I'll take the terminal boundary. Just set to n. It's the -7. It always seems to throw it off because we're adding in the specific dimensionality and stuff there. And oh my god. Wow, this is very, very embarrassing. Oh well. Let's take the actual mass of the neutron and mass of muon. Wait, that is the mass of the neutron, isn't it? It's not something else. That's a neutron, blah, blah, blah. And oh, that's a big N. Huh. It's very interesting. It's a particle. Wow. I'm using the wrong factors here. See, this is why you're supposed to work through all of it, and you're not supposed to cheat. Wow. So neutron, bye-bye. So electron. Wait a second. Again, sure somebody already knows this, but boom. Copy that. Do that. Oh, wait. I believe this is what we're supposed to do. This is already here. A little bit larger, but okay. I saw that with the electron, the proton, and mass. It's kind of close. Not quite. I do far too much numerology. Okay, we're just going to do this instead. Hold on. No. We're going to figure this out. turn into this. Because that's just what we're gonna do. Okay. Mass form. Ooh. 7. There we go. Okay. Oh, okay. So square root of b, which is 7 times margin thing. Okay. Keep on exponentiating that. We multiply that by 1. 1. And the mass. Oh my god. Particle notation. Oh my god. Wow. This is confusing. It's the mass of give me a number. Okay, we're just gonna do this. Proton. Get our electrons here. Okay. Okay, so we got that. And we need mass of U1. Look at the right subscript. Okay. That. Beep. No, help. Text. That, blah, blah, blah. Boom. Boom. Cool. Go in here. Ooh. Oh my god. What did I even do? Hold on. So they're managing. Whoa, that's all wonky. Okay. Times J1. Okay. Get J1. Throw this in here. Oh my god. Okay. Does it not want to do this for me? Does it not want to copy and paste from screen to screen? Oh no. Be highly inconvenient. Okay. I'm just going to take the result. This is far too much work. Okay. That's the result. We'll take a bunch of decimal places. Cool. Okay. We have that part. Swan, secant, cotangent, 2 gamma, 5, divided by 7, and then we'll change this to doesn't let me select it all. Oh, no. All right, 10 to the negative 7. Bracket. Okay. Far much more work than I was. No! Okay. We're getting lazy. We'll do this. We'll do this on our own now that we've lost everyone else. Hold on, there is a solution here. Stop sharing that. I know there is. We'll do the original. I have it in an email. Oh, wait, no. I actually have it over here. Because of reasons. Terrible at spelling. Where are we? Structure constant, hyperbolic vortex equation. Here we go. Okay. No. We want to have the right syntax, right? This is the original version. All right, this is the first edition. This doesn't have a monogens thing. I need to work on. And then all done. Boom. Okay. Oh, look. I'm pretty sure that was the moment measured. Did all the significant digits and then some. And I got a little bit more beautiful. But yeah, I should really just, yeah. Okay, these things happen. But that's all I got for right now. Is see a monkey and everything. But hey, these things happen. But cherry Coke, it's a wonderful thing, but that's all I got. Peace out, everybody. Be safe. You never know what's going to happen. Take care of yourself.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.